Hey guys, so today we are trying to prove Euclid's proposition, book 3, proposition 16. And in this proposition, we're trying to prove a lot of things. So we're given ABC, the circle ABC, and we know that C is the center and AB is the diameter. So that's the diameter and that's the center. But we're trying to prove a lot of things. So the first thing we're trying to prove is that if you draw a straight line off of A perpendicular to BC, then that line will not fall inside the circle or on the circle. So line from A at a right angle to BC will not fall in or on circle ABC. So to do that, he first proves that it will not fall in circle ABC. So he starts off by using a reductio ad absurdum and assuming that it will fall inside the circle. So he connects A and C. And the reason for this is assumption, because we're going to use the reductio ad absurdum. And then he connects D and C, and he can do that because of postulate 1, which says that you can connect any two dots, any 2 points. So now that we've drawn DC, we know that DC is equal to DA, and we know this because of definition 15. And definition 15 is the definition of a circle, which says that if you have any line falling from the center to the outside of the circle, that it is equal to any other line falling from the center of the circle to the outside of the circle. So we know that DC and DA are equal. And since we know that DC and DA are equal, we know this is an isosceles triangle. And proposition 5 says that in any isosceles triangle, the bases, the angles at the base are equal. So angle DCA and angle DAC are the angles at the base, and those are equal. So now we know that these angles are equal. And we also, so now we can move on and we can say that angle DAC is a right angle. Here, I'm going to rewrite that. We know that DCA is equal to a right angle DCA. And we know that because in the beginning when we drew AC, it made DCA a right angle. So that's from step 1. And since DCA is a right angle, we know that DAC is equal to a right angle because of common notion 1, which says that if DCA equals DAC and DCA equals a right angle, then DAC equals a right angle. But we come to a problem because proposition 17 says that in any triangle, the sum of any 2 angles must equal less than 2 right angles. But since these two angles in the triangle are equal to 2 right angles, even though proposition 17 says that angle DAC plus angle DCA should be less than 2 right angles, we have a problem. So we can use the reductio ad absurdum. So we come to a problem. So because of reductio ad absurdum, we know that this is false because it is what we assumed. So there cannot be AC. which means that the line from A that is at a right angle to BC will not fall in the circle ABC, and similarly, so this says that the line from A that is at a right angle to BA will not fall inside the circle. Similarly, we can prove that the line from A that is at a right angle to BA will not fall on the circle. Which means that the only alternative is that the line from A that is at a right angle to BA will fall outside the circle. So next we draw that line. So let's call it AE. And we're going to draw, I'll just draw it. So we can draw AE. And we are going to use Proposition 11. And Proposition 11 says that if you have a line and a point on that line, you can raise a perpendicular line to it. Okay. So the next thing that Euclid tries to prove, which he does prove, is that there cannot be another straight line in between EA and CHA, which is, this is H. So there cannot be another straight line that falls in between EA and CHA placed in here. That will not fall in or on the circle. So the next thing he does is he draws DG, and he draws DG at a, he draws, sorry. Okay. So after he draws AE, he is moving on to try to prove that another line cannot fall in between. So he uses another reductio ad absurdum to assume that there is another line that falls in between AE and CHA. So that we'll call FAF. And so he assumes that. So after he assumes that, he draws line DG, and he draws line DG. So that point is G. So he draws line DG, and he draws it at a right angle and perpendicular to FA. So from point D and perpendicular to AF, and he uses Proposition 12, Book 1, Proposition 12, which says that you can raise a perpendicular line. So after he does that, we know that angle AGD, this angle, is a right angle because of Proposition 11. Because of Proposition 12, we also know that angle AGD is a right angle because we set it to be perpendicular to that line. So the next thing he does, now that we know this is a right angle, we must assume, or we have to know, that DAG, angle DAG, has to be less than a right angle because two angles in a triangle cannot add up to more than two right angles. And that's from Proposition 17. So we know that this is a right angle, and this has to be less than a right angle. And because we know that, we can use Proposition 19. And Proposition 19 says that in any triangle, the side opposite to the greater angle is the greater side. So because angle AGD is a right angle and angle DAG is less than a right angle, angle AGD, which is this AGD, which is this one right here, is greater than this one, which means that line AD is greater than line GD. And that is because of Proposition 19. And we know because of definition 15, which is the definition of a circle, which says that any line from the center of the circle to the outside of the circle is equal to any other line from the center of the circle to the outside of the circle. We know that DA is equal to DH. So we can substitute DH for DA. So we can say that DH is greater than GD, and that's because of common notion 1. But since it's an inequality, we call it common notion 1.1. So we know that DH is greater than DG, but here we encounter a problem because line DG is greater than line DH because of common notion 5. And common notion 5 says that common notion 5 says that the whole is greater than the parts. So the whole line DG is greater than the part of the line DH. So that's common notion 5. So these two things cannot be true at the same time because they contradict each other. So we use reductio ad absurdum. We have our problem. We have a reductio ad absurdum. So we know that this must be false because it is the thing that we assumed. So AF is not true. And that means that this line cannot be here, AF cannot be here, and any other line inserted in between EA and CHA cannot exist. So the final thing that Euclid proves is that the angle between BA and CHA is greater than any acute angle, and the angle between EA and CHA is less than any acute angle. And he does this, he doesn't really use anything, he just uses a reductio ad absurdum, but he says it with words instead of proof, so I'll just explain it. So he uses a reductio ad absurdum in words. So he says, let's start by assuming that AF is a line and that it is a straight line that falls outside the circle that's in between AE and CHA. So he says that because AF is there, BA and AF, the angle between BA and AF, is greater than the angle between BA and CHA, and the angle between EA and AF is less than the angle between EA and CHA. But because AF cannot be there and no other line can be inserted in between EA and CHA, that means that BA, the angle between BA and CHA, is the greatest it can be, and that is greater than any acute angle. And the angle between EA and CHA is the smallest it can be, and that means it is smaller than any acute angle. And so that is all he's trying to prove. So QED, and there you go.